Hello, Professor Zhang. This is our group presentation for the ball and beam project. All right, so we're going to start off with our data from our real-world experiment where we actually ran the ball and beam and collected the position over time. So in this graph, you can see it starts at the 2-inch mark, makes it up to 7, overshoots, oscillates a little bit, and then comes to steady state in a little over 5 seconds, and it hovers at like 7 1/8. And then around 20 seconds, we got our big disturbance down to like 2.75. It comes back, overshoots 7, and then it comes back to steady state, and it hovers around like 7.2. All right, for the second trial, we start at 7, and then we go all the way up to 10. It actually doesn't overshoot. It hangs right there at like 9.95. And then around 17 seconds, we have our disturbance. The ball moves almost up to 12, and then it comes down, overshoots 10, and then it hovers around like 10.2. All right, and lastly, for our third trial, the ball starts at 10, and then we move the potentiometer to 4. It goes down, overshoots 4, comes back up, and achieves steady state around like 7 seconds. And it hovers around like 4.1. And then at 16 seconds, we have our other disturbance. It goes down to like 2.25, overshoots, and then comes back riding very close to the 4-inch mark. All right, so next we're going to talk about our block diagram.
So in our block diagram, our reference is the input from the hard potentiometer. Our controller is the Arduino using PID control. That signal goes to the actuator, which is our servo and linkage assembly. And that will go to the plant, which is the ball and beam. Additionally, our feedback is our soft potentiometer, which analyzes the real-time distance the ball is at and feeds back the signal to the controller for the PID. Also, we have our disturbance, which is the pencil when we push the ball away from the desired distance.
So one of the things we had to establish is the relationships in our specific ball and beam design. So in our ball and beam design, for every 1 degree that we tilt the beam, it corresponds to a 5-degree change on the servo head, whether it be in the positive direction or the negative direction. So we also need to establish the relationship between the soft potentiometer value, because the soft potentiometer starts at a length of 20 inches, and we only care about 12 inches of those 20 inches. So in order to map the soft potentiometer values, we have the value given to us, which is a value between 0 and 1023, and then we multiply that by 20 and divide by 1023, and that should give us a value between 0 and 20 to know where the ball is in reference to our soft potentiometer. An important thing to note when we're looking at like our moments or our torques is to know that our fulcrum is 8 inches away from the lever arm, which is where our linkage rests, along with our servo. And we also need to map our hard potentiometer, and that one is a linear conversion where we just multiply the value given to us from the hard potentiometer, which is again a value between 0 and 1023. We're going to multiply that by 12 and then divide by 1023 in order to give us a value between 0 and 12, which will correspond to our values on our laser cut dial.
All right, and as you can see here, here's our governing equations. The top one is our governing equation for torque balance, and our bottom one is our equation for the simplified force balance equation. And for all this, we have to remember that for small values of theta, sine of theta is approximately theta, as well as for small values of theta dot squared is approximately 0. And finally, the moment of inertia for a sphere is approximately 2/5 mr squared. Again, 2/5 mass times radius squared.
Okay, so here we have the block diagrams that we created in Simulink. As you can see, we use the KP value of 0.25, a KI value of 0.0001, and a KD value of 0.7. We use our mechanical advantage, 1/5. And on the bottom, you can see the subsystem for the ball and beam model. And so with this Simulink diagram, we created our 3 plots, and each time we changed the initial position and the target position. And now we'll go to the plots. Here's the first plot. The ball started at the 2-inch mark, and it went up to 7 inches, and it settled within roughly 14 seconds. And then at the 20-second mark, we applied the disturbance of over 1 inch, and it settled back to that in approximately 10 seconds. And the second plot, it started at the 7-inch mark and went up to 10, and it did that in roughly 8 seconds. And then at the 20-inch mark, again, we had the disturbance of 1 inch, and it settled back to the 10-inch mark in 10 seconds. And the third and final plot, it went from the 10-inch mark to the 4-inch mark, and it did that in roughly 10 seconds. And then at 20 seconds, the disturbance was once again applied, and it settled back to the 4-inch mark in approximately 10 seconds.
All right, and this was our presentation. Thank you for watching, and have a great day.